Now we're going to take a look at, rather than adding or subtracting things to the function or inside the function, we're going to look at what if you are multiplying or dividing. So let's start with, we're going to use this function. It's something you're going to look at more in the next uh, course. However, this function actually really shows this nicely. It's sine of x, and sine of x is this nice little wavy type equation here. And we're going to first take a look at having this function as f of x equals, and we're going to put an a in front of the sine x. This is as if you were multiplying the sine of x, or this function here, by a. So I'm going to make a slider for a. Right now, notice that this is green, and green just covered up our red graph. And that's because a is 1, and when you take 1 and multiply it by sine of x, you get sine of x. So we're going to see what happens when you make this larger. Now we're going to first I'm going to drag it so it stays positive, and we're going to see what happens when it gets larger than 1. So notice that, look at what happens. What's happening to this graph? Notice that as it's larger than 1, it's getting stretched up really far. Now I'm going to make it stop at a nice neat number. Let's get it to stop at 6. And let's examine what we had before. So if I click on this sine of x, we're going to choose a point, say this one right here. Notice that this one right here has a y-coordinate of 1. Now that same point on the green one was this one here. So the 1 got moved up to where it is now this 6 here that you see. And notice, what is our A? Our A is 6. And that 1 got stretched up. In fact, you can see the whole graph getting stretched up so it's taller. Let's go ahead and examine another point and see if the same thing happened. If that y-coordinate was multiplied by that 6 and got quite large. So let's take a look at, say, this one. That's at -1, and the corresponding green one is way down here, and notice its y-coordinate is -6. If you take -1, the y-coordinate, and multiply it by a 6, you get -6. So what that 6 did, or whatever the A did, is as we went bigger than 1, it stretched it up. Now notice I'm still bigger and taller than the other, even though I'm making my A smaller. If I stop at 4, let's see what happens. Now notice my y-coordinate is 4, and the original one was at 1 here. Over here, your original one is 1, and the green graph is at 4. So what happens if we go below 1? Let's go back down to where we're at 1. We're now at 1, and it's the same. Now, as we go below 1, what's happening to the graph? That green graph is shrinking. It's getting smaller. We call that a vertical compression. So what we had before, when it was getting taller, was a vertical stretch. This is a vertical compression. And notice that that happens all the way down until we're at 0. And 0 times sine of x is going to be 0. So notice we just got a straight line right at the x-axis. What's going to happen when it becomes negative? Oh my goodness. Watch what happened. I'm going to stop at -1. -1 times sine of x would just be negative sine x. And notice, if you look at this, it looks like this point right here on the original graph flipped over the x-axis and became this one up here. This one here flipped over the x-axis and became this one down here. So what we changed is we changed the sign on our y-coordinate when we multiplied by -1, and that flipped it over the x-axis. So your A, as it gets larger, it stretches it up as it goes between 0 and 1, it compresses it down towards the x-axis, and when it's negative, it flips it over the x-axis. We'll summarize all of this at the end. Now, that was multiplying something on the outside. What if instead of having this, we multiply something on the inside, which would be, we'll call it b. So I'm going to make a slider for b. Notice b is at 1, and now we have the same exact graph as our red graph, which is our standard graph. The 1 times x, if b was 1, would give you x, and that's the same thing we have on the red one. Now, watch as I make b go larger. Oh my goodness, it's not stretching up at all. It's actually not stretching out either. It looks like it's condensing it. It's like a spring, squishing it in towards the y-axis. Now what happens as we get smaller? Now I'm going to stay positive. We're going to examine on a different function what happens if we go negative. But I'm going to get back to 1. And then what if I go between 0 and 1? It stretched out and it got longer. Now, let's examine kind of what happens here. Let's go to some nice number that's bigger than 1 first. How about if we stop at 2? Now, if we stop at 2, we have this wavy pattern that keeps repeating itself. Let's examine one wave of the original red graph. So we're going to examine one wave which starts here and goes to here. So that wave is from here to here on the original graph. Let's take a look at the green graph. How many waves do we get in that time period? Notice we get 1 wave, 2 waves that happen in the same time the original graph did 1. That's what that 2 is doing. It's making things happen twice as fast. When something happens twice as fast, it takes half the time for it to happen. Now, if that's the case, when we examine these points, the x-coordinates for that correspond to each other, the x-coordinate on the green one should be half of that corresponding one on the red one. Let's see if that's actually the case. I can actually click on this point right here. This is the end of one wave on the red one. That point has an x-coordinate of 2 pi. If it takes half the time for things to happen on our green one, that corresponding spot where one wave ends should be half the distance. So instead of being 2 pi, if you divide 2 pi by 2 or multiply it by a half, we should have 1 pi. So let's look at the green graph. One wave on the green graph goes here and stops right there. And notice that point where it stops, the x-coordinate is pi. If I were to take that 2 pi and divide it by my b value, which right now is 2, notice I get pi. And that is where the x-coordinate is that corresponds on your original graph. It took half as long. Now, if I had this at 4, it should, instead of being dividing by 2 here, if the b is 4, I should be dividing by 4 there. Let me clear everything and change this b to 4. And let's see what happens. How many waves do we get in that one wave? We're going to go to 4. So now let's check it out. One wave on the red one stops here. How many waves on the green one do we get in that time? We get 1, 2, 3, 4 of them, which means it takes 1/4 the time for a single wave to happen. one single wave when the b is 4 happens in that little area there. Let's check this corresponding point right here for where our, and actually let me clear my drawing so you can see the point a little better. This point here is where one wave of the red one ends. One wave of the green one ends right here. And notice that that's pi over 2. Let's check that out. Now what we were discussing was that we should be able to take our x-coordinate and divide it by b. So if that's the case, my x-coordinate here is 2 pi. My new x-coordinate, because b was 4, should be 2 pi divided by 4. But that doesn't look like this. Notice, though, we can reduce it. 2 over 4 can be reduced. You can divide a 2 into the 2 and get a 1, and into the 4 and get a 2. And that makes the pi over 2. So it looks like, yes, if I took this x-coordinate and divided it by my b value of 4, I would get this coordinate, which is my new x-coordinate, from compressing this in. Now notice we have a b bigger than 1, but rather than stretching, we're compressing because things are happening faster when you multiply the x-coordinate by a bigger number. What happens if I have the b small? So let me go ahead and make this less than 1. And let's do a nice number. We're going to do 0.5 because that's a half. So this is 0.5. Now this is going to be a little bit harder to see. So we're going to go ahead and kind of take a look at, actually I'm going to move my graph and that'll make it easier. We're going to move our graph over because we need to be able to see an entire wave on the green one. Now, let's trace an entire wave on the green one. It's taking longer because the b is less than 1. It's taking longer. It's going from here all the way over to there for our green one, our new one, to actually make one of those waves. Now let's look at how many of the waves of the original one happen in that time. So I'm going to change colors here. And let's trace the red one. We get 1 wave and 2 waves. 2 waves in the same amount of time, and our b was 0.5. So we actually had f of x equals sine of 1/2 x, because 0.5 would be 1/2. And that means that we only got half of one of these waves in the same amount of time it took to do 1 wave on the original one, which means it's going to take twice as long for your wave. And notice we have 2 of the original ones in the time that it took to do 1 of the new ones. Let's examine some of the points then. What does that mean for us? The end of our new graph is way over here at 4 pi. But the end of one wave on our original graph was here. Notice, what would you do to 2 pi to move it over to the 4 pi? You would multiply it by 2. Well, how does that relate to a 0.5? 0.5 is the same thing as 1/2. Notice before, when we were compressing things in, we were able to take that x-coordinate that we had here, which was 2 pi, and we were able to divide it by our b. Let's see if that still works for us. So 2 pi divided by 0.5, isn't that the same thing as 2 pi divided by 1/2? And when you divide by fractions, you flip and multiply. So that's 2 pi times 2 over 1, which means that's the same thing as 4 pi. And notice, where did the corresponding point for the end of our one wave on our green cycle happen? It stopped way out here with an x-coordinate of 4 pi. So when we had a very small b that stretched it out, and when you had a very large b, it shrunk it in or compressed it in. And for the b, what you want to do to figure out where your new point is, you're going to take your x-coordinate and you're going to divide it by that value, and that tells you where your new one is. If you had an a out front before, you would multiply by it. Now let's take and do a different graph real quick to see what happens if your b is negative. So I'm going to change this to x cubed because we can see this a little bit easier there. So this is going to be, we're going to have bx, that whole thing in parentheses, cubed. And I'm going to go ahead and clear out these. And I want you to see what happens when the b is negative. In fact, actually, we don't really need a slider for it. I'm just going to change this b so that it's -1. Notice what happened. We flipped. And it's kind of hard to tell, did we flip over the x or did we flip over the y? But I want you to think about something. Right here, if you're multiplying your x by a negative, let's say your x was over here at this spot. If you multiply your x by a negative, what's going to happen? It's going to flip over to this spot and change its sign. So when you have a negative b, what that does is it flips it over the y-axis. And that's what happens with your transformations. Now let's kind of summarize this. Let's say that you have a function, and actually we're going to just go ahead and x these out. Let's say you have a random function, g of x, and g of x is changing f. So you could have a number outside multiplied by f. You could have a number inside multiplied by the x. This a right here is going to either vertically stretch or compress. If the a is a large number, it will stretch. If the a is a small number, it will compress. So if your a is greater than 1, it's going to be a stretch. If your a is less than 1 and bigger than 0, in fact, actually on both of these you could do the absolute value of it, then that is going to compress it down. If your a is negative, then it's going to reflect your graph over the x-axis. So that's what the a is going to do. Now your b is different. The b is a horizontal stretch or compress. And if your b is going to be, actually I'm going to change colors so we can see a little bit better because it's going to kind of overlap. Actually, we'll do red. If your b is greater than 1, so your absolute value of b is greater than 1, it's actually compression. And you're actually going to take your x-coordinates and you're going to divide by that b. If the absolute value of b is less than 1 and greater than 0, then that's going to be a stretch. It's going to make things take longer. And you're still going to do your x-coordinate divided by the b, and you're going to find that that makes a bigger number. And if your b is negative, you're going to reflect over the y. And that's a summary of what those two do, because those are a little bit harder to see than the other. If you have an h, you're going to go left or right, and that would be inside. If you have a k added on the end, you're going to go up or down.